click that button. All right, so the ideal gas law, PV equals nRT. Oop, I didn't want to do that. That was messed up. PV equals nRT. And there's values for R, the ideal gas constant, depending upon which which value or which unit the pressure is in. So we want to find the molar volume or the volume of gas at STP. Use the ideal gas law on standard temperature and standard pressure. Hey, that's cool. Have the what? Nate, yeah. Yeah, I think Nate has all the rest. Okay. He has them up in C large. Okay, thanks. No problem. Okay, so you know this idea, the standard molar volume, that is Avogadro's law. Avogadro's law is that 1 mole of a gas is equal to 22.4 liters. I told you that, and you kind of believed it, I guess, but I'll show you that it is 22.4 liters. In other words, this ideal gas law, PV equals nRT, if I write PV equals nRT and solve it for V, so that V is equal to nRT over P, and what I want to do is figure out what's the volume for 1 mole at standard temperature and standard pressure. And so if I substitute 1 mole for N, and it doesn't matter what value R I pick, except that the pressure unit has to be the same as the pressure unit in the value for the ideal gas constant. So you know that the standard temperature and pressure condition is 1 atmosphere and 0 degrees Celsius. 0 degrees Celsius is 273 Kelvin. So if I pick a value for R that has the unit atmosphere, that's this 0.08206, 0.08206. That just has more significant figures than the value I gave you yesterday, per mole Kelvin, times the temperature. But the temperature's got to be in Kelvin, 273 Kelvin, and a pressure of 1 atmosphere. Well, the 1 mole in 1 atmosphere, those aren't very exciting numbers, but the 0.08206, 0.08206 times 273, 22.4 liters. So you already know, because the only thing we did with gases before this whole thing about the gas unit and the ideal gas law is I just told you what Avogadro's law is. That's that at STP, 1 mole of gas has a volume of 22.4 liters. But now here's a proof of it, that if you have a mole of gas at 273 Kelvin, 1 atmosphere, and you pick a value for R that has the same unit, like this pressure unit is the same as the pressure unit in the denominator, you get 22.4. You could also use like 62.36 millimeters of mercury liter per mole Kelvin, so long as you use 1 atmosphere of pressure in millimeters of mercury, or use 8.314, but with the pressure in kilopascals. Like that's the same thing. It's just kind of like overkill to use the ideal gas law if the conditions are STP conditions. But we try to adjust things to standard temperature and pressure, because then you could just use a conversion factor that moles 22.4 liters. All right. Ugh, I'm tired. I need a nap. All right, so at STP, what's the volume of 2.5 moles? So there's 2 ways to do this problem now. One way is to just use the conversion factor that 2.5 moles, or that 1 mole of a gas has a volume of 22.4 liters. So if you go like 2.5 moles times 22.4 liters, it's 56 liters. Or the other way to do it is by using the ideal gas law, PV equals nRT, where V is equal to nRT over P. So I got 2.5 moles times the ideal gas constant. I mean, if you do it in atmospheres, 0.08206 liter atmosphere per mole Kelvin. times the temperature, 273 Kelvin, divided by the pressure, 1 atmosphere, you get the same thing, 56.0 liters. But the thing to remember is that this conversion factor, this is only at STP, only when the temperature is 0 Celsius and the pressure is 1 atmosphere. But the ideal gas law works at all temperature and pressure conditions. So you can never go wrong with the ideal gas law. The ideal gas law is very, very useful. In fact, when we do work with gases in thermodynamics, in AP physics, and in like AP chemistry, we pretty much only use the ideal gas law because you can derive the combined gas law from it, and you can adjust everything to STP with the ideal gas law. So the ideal gas law is actually a really, really, really fundamental law that works under all conditions if you apply it right. All right, so number 1 and number 2 are pretty much the same, but number 2 is just a proof that if you had 2.5 moles, you could do it in 1 of 2 different ways. All right, then at the bottom of the page, there's 2 different containers. So you got 1/10 of a mole of nitrogen and 1/10 of a mole of hydrogen, and they both occupy the same volume, and they both have the same temperature. So the question is the pressure in the container with the hydrogen less than, greater to, or equal to the pressure in the container with nitrogen? So it seems like everything's the same about the 2 gases, except for which gas is present. In other words, in one case it's nitrogen, in the other case it's hydrogen. We're trying to figure out a pressure. So the ideal gas law, PV equals nRT. If you want to find the pressure, that's P. P is just equal to nRT over V. So what the pressure depends upon is the number of moles of gas, the ideal gas constant, the temperature, and the volume. But what's not in the equation is like the formula mass. It doesn't matter if it's nitrogen or if it's hydrogen. So it doesn't matter which one you pick, but I'll show you that there is one difference. The number of moles is 1/10 of a mole. Because the problem doesn't say what pressure the pressure needs to be in, it kind of doesn't make a difference what the pressure unit comes out to be. But if I pick a value R, like I'll use a different one. How about like the third one, 8.314 kilopascal liter per mole Kelvin. If I choose to use this value for the ideal gas constant, the pressure unit is kilopascal, so then the unit for the pressure will be in kilopascals. The temperature is 298 Kelvin, and the volume is a liter. Let's see, times 0.1 times 298. It's like, yeah, that's right, 248. And the unit would be kilopascal, because whatever the unit for the pressure is in the ideal gas constant is the unit for the pressure in the answer. It would be totally okay to pick a different value R, but what's important is that the pressure unit match the pressure unit that's in the ideal gas constant. Now, if instead I want to do hydrogen, well, hydrogen, it's the same 1/10 of a mole. What is going to be different is the masses of the gases. So the idea with Avogadro's law is that at STP, or at any temperature pressure condition, the same 2 volumes of gases will have the same number of particles. What is going to be different is the masses will be different. The mass of this gas, you could figure out, because if you did 1/10 of a mole, that's the quantity of hydrogen. Every mole of hydrogen has a mass of 2.02 grams. That's going to be 0.20 grams, like 0.202 grams. But the nitrogen gas, it has a higher mass. So 1/10 of a mole of nitrogen, every mole of nitrogen is like 28.02 grams. So that's 2.80 grams. The mass of the nitrogen gas is going to be about 14 times bigger than the mass of the hydrogen gas, but the quantity of particles is exactly the same, uh, or the volume of the particles is the same at the same pressure and temperature condition. What you got to remember is that in all gases, they're individual particles that are not in contact with each other, but they bounce off each other, they hit the walls of the container, they push on this piston here that's movable apparently, and as a result of the motion of the particles, because they're separated by some kind of distance, they exert a force on the outside of the container or a pressure. They also push up on this piston, maybe a movable piston, like the lid of the container can move up and down. But there's lots of space in between them. And at the same temperature, every one of those particles has the same kinetic energy, we say. So it turns out that in the nitrogen gas, the particles aren't moving very fast. They might have some kind of a speed, but those same number of particles taking up the same amount of space, these particles in the hydrogen, because they have a lower amount of mass, they have to be moving faster. So these particles actually have a higher speed. They got the same energy, but they have to have a higher speed. And they have a lower amount of mass to be able to hold that lid of the container at the same position. But no matter what, the same number of particles take up the same volume at the same temperature. So is the pressure holding the hydrogen greater than, less than, or equal to the pressure of the nitrogen? Well, the pressures are exactly the same. And one way to justify that is that in the equation, there's nowhere to put like the formula mass. It doesn't matter that it's nitrogen or matter that it's hydrogen. It's just how many particles, what's the temperature, and what's the volume. We find that to be true for all gases. That's actually where Avogadro's constant, the 6.02 times 10 to the 23rd, comes from, is from understanding that different different types of gases or different particles of gases have the same quantity for the same volume at the same temperature and pressure all the time. So it could we could live in a universe that's not like that, and it would be more complicated, but it's actually quite simple. The world comes out to be that way. All right. So here's another issue. A lot of times we measure volumes of gases in the laboratory. You measure the volume of the gas and you know the pressure and temperature. And from that, you got to figure out how much mass of gas is present. You can't just weigh gases on balances. So one thing that we did all the time in basic stoichiometry is if you had a quantity that was not in moles, you wanted to convert to moles first, and then use like mole ratios, and then convert away from moles. So converting to moles is important. Um, in this problem, you already know how to do step A. Like if I've got 22.4 liters of methane at STP, the first thing you want to try to do is convert to moles. This happens to be the volume of 1 mole of gas. But if you're at STP, 1 mole has a volume of 22.4 liters. So if you want to convert to moles first, the first thing you can do is just use like Avogadro's law to convert to number of moles. If this happened to be like a different volume, it wouldn't matter. You just put that different volume here. It's cool. Yeah. They weren't calling you to give you an offer on your car's extended warranty? No. There's a dude in fifth period, and he plays with that extended warranty people all the time. Like he'll take the call and then tell them what car he's got. They go through the whole thing, but he doesn't have that car. He just makes up a car. All right, so if you want to convert into grams, use the formula mass. So methane, we did this yesterday, but you got a carbon and you got 4 hydrogens. Carbon's 12.01, hydrogen's 1.01, I think. Let me make sure. I'm gonna use the numbers that are like on your periodic table, that are on the like in the course thing, so that it's the same. Let's see, course, Chem 1. I just know formula masses, but we've got them rounded to fewer significant figures on the official WAHS periodic table. Yeah, 12.01, 1.01, that's good. Hold on, I gotta move these over. Let's see, where did my thing go? Let's see. I hate when that goes away. Oh, there it is, stylus. Gotta slide that over. There we go. So that's 12.01, and this is 4.04. Those add up to be 16.05. So the formula mass is 16.05 grams. So if I want to convert from, well, this is just 16.05 grams then, 16.0. It happens to be 1 molar volume. But if you don't have standard temperature and pressure conditions, you can't use Avogadro's law. So this conversion factor here, this is Avogadro's law, like we used back in March, and that's only at STP conditions, which is the only kind of condition that I told you about back when we did stoichiometry involving quantities with gases. But now, here's a volume of a gas, and it's like it's 1 atmosphere and 0 degrees Celsius, which is still STP conditions, and you can use Avogadro's law, but you could also use the ideal gas law. So if it happens to not be at STP conditions, another option is, and it works at all conditions, a number of moles is equal to PV over RT if the pressure is 1 atmosphere, and then the volume is 2.20 liters. And then I got to use an ideal gas constant that has the unit of atmosphere, and that's the 0.08206 atmosphere liter per mole Kelvin. And then you got to be careful with temperatures all the time. This temperature can't be in Celsius, it has to be in Kelvin. 0 Celsius is 273 Kelvin. I don't know, let's see. 2.2 divided by 0.08206 and divided by 273. 0.0982. And if you get a quantity in moles, you can then just convert that into liters using the formula mass. So 0.0982 moles. Every mole of its CO2 has a certain mass. So you can figure out the mass of CO2. Let's see. CO, I got 1 carbon, I got 2 oxygens. Carbon is 12.01 grams. Oxygen is 16.0. Anytime you got to convert from mass into moles, you got to use the formula mass. So that's 12.01 grams. This is 32.0 grams. 44.01 grams. .32. So the alternative way, instead of using, and the ideal gas law works for all temperature or pressure conditions. This happens to be at STP. So your other option, because it's at standard temperature and pressure, is 2 liters, and you can use Avogadro's law. 22.4 liters is the same as a mole, and you'll find that that is the same number of moles, 0.0982 moles. Anyway, so if you're at STP conditions, you can convert from the volume into moles and then from moles into mass using the formula mass. You have to look up the formula mass. add up the mass of the sulfur and 2 oxygens and whatnot. All right, so you can do the last one on your own, and then this quick check, it just says if I have an unknown quantity of a gas, don't know what the quantity is. In other words, that's a number of moles. I know the temperature, I know the volume, I know the pressure. How many moles of gas is that? And that problem is the problem that's in the quick check. Here, let me show you. Let's go to show desktop. Here, it's on the right-hand side of the course page in the upcoming. But you can get that done now, and then that's that. Let's see. I don't know, setup questions. So it is 2 questions, one of them about which R value would you use, and then what's the number of moles of gas that you finally get as the result. And then the other problem that I'll go over like right at the end is from yesterday, there was that one last problem that we didn't get to. And let me see if I can. Oh, there goes that. At the end of the worksheet from yesterday, actually, maybe we'll just go over this right now. So you have one more example. See if we can find it. Yeah, the one from yesterday uh, is about gas in a scuba, a container for scuba. Scuba is an acronym. You know what it stands for? Can you guess some of the words? Ooh, no, that's good. The U is related to submerged. Underwater, yep. It is. Breathing. A is for apparatus. And it's all together in one thing. Self-contained. Somebody's got that Google. It's okay. I mean, if you know, you know. Self-contained underwater breathing apparatus. Or like, what laser is? That's the light amplification by the stimulated emission of radiation. Or laser. Isn't that exciting? Think what other good science ones there are. Well, what precedes laser is maser, which is actually microwave amplification by the stimulated emission of radiation. And then, but it's not always microwaves, it could be light. So we get laser. Scuba, its invention is kind of, a lot of things are invented by many people in parallel ways, but then Jacques Cousteau, who's a great oceanographer, is credited generally with the full scuba. Scuba is not only used in, diving, but also like firefighters. You got a self-contained mask. You just go into a fire and uh, not breathe the smoke. It's just the same as you can go underwater and not have to worry about water getting in there and aspirating water. It works just as well and actually a lot easier if you're in a smoke-filled room. Just got to keep the smoke out of the mask. Just same as you keep water out of the mask. You can still breathe. All right, so anyway, you got this canister. You got 30 liters of gas, and the temperature is 300 Kelvin, and the pressure is very high, 50, 65 kilopascal. So how many moles of gas? From the ideal gas law, PV equals nRT. The number of moles is PV over RT. So the pressure is 50, 65 kilopascal. The volume, 30 liters. The ideal gas constant you want to use is whichever one has the unit for pressure that's in kilopascal. Yeah, it's got 8.314 liter kilopascal,